This work was about a computational model of the cerebellum granular layer, its properties and plasticity. The properties we focused on and wanted to reproduce were the high-pass filter, the time windowing effect, the center surround organization, and the coherent oscillations. To test these properties, we used a particular spiky neural network with elements positioned and connected in a 3D scaffold according to physiological findings. This network was provided by the University of Pavia. The results of this test were positive for the high-pass filter, the time windowing effect, and the center surround organization. But we did not get relevant results for the coherent oscillations. For the plasticity, we focused on the spike timing dependent plasticity, or STDP, that updates the synaptic weight value according to the time difference between post and presynaptic spikes. In particular, we focused on the eSTDP that was already implemented in our simulator and the iSTDP that was not present in the simulator and was implemented by us. We also focused on the mossy fiber granule cell synapse, which was not present in the simulator and was implemented by us as well. This specific synapse has a time dependency similar to the eSTDP one and a frequency dependency that will change the amplitude of the learning rule according to the modulation frequency of the input. To test the eSTDP and iSTDP, we inserted them in a simplified network to see if they would allow the network to memorize a specific pattern. For this test, we divided the time into 8 blocks, and for each one we computed the Golgi power, which evaluates the learning amount. In particular, this value is equal to 0.2 if there is no learning, and it will increase up to a maximum of 1 if the network learns. As you can see from the graph, we were able to make the network learn a pattern. For the mossy fiber granule cell synapse, we focused on its ability to detect the input modulation frequency, with 2 different inputs, a pure burst and a burst with a 5 Hz noise superimposed. In the first case, we obtain very high accuracy and precision, while for the second input type, we lose accuracy and precision, especially at the higher frequencies. To conclude, for the physiological properties, we were able to reproduce the high-pass filter, the time windowing effect, and the center surround organization quite well, but we were not able to reproduce the coherent oscillations property. For the new synapse implementation, we got satisfying results for both iSTDP and mossy fiber granule cell synapse. There is still room for improvements though. In fact, for the physiological properties, we should find a better way to evaluate the oscillatory response and use a bigger and more realistic network. For the new synapse implementation, it would be possible to use a larger and more complex network for the memorization of multiple patterns, and wait for more in vivo results for the mossy fiber granule cell synapse.